Welcome, Hornets, and thank you for joining me today. Today we're going to be taking a look at using DeMoivre's theorem in order to find all of the imaginary roots and roots of a polynomial. Now on your screen you'll notice that we're looking at x cubed minus 8. And if we were attempting to factor this, you'll notice that we would have x minus 2. We're looking at a difference of cubes. So we have x squared, we have plus 2x, and then we have plus 4. And you'll notice that we get one root that's a positive 2 here, and the other one requires us to use the quadratic formula. In this case, negative 2 over 2 plus or minus the square root. And then we have this 2 squared, 4, minus 4 times 4 is 16, divided by 2. This gives us negative 1 plus or minus, and we're now looking at the square root of 12, which would give us root 3i. Now, this is fine and dandy. If we look at the locations on a complex plane, you'll notice that we find one of them, and one of them is at positive 2 here. The other is going to be in the second quadrant, somewhere around, give or take here. And then we have a negative 1 and a negative root 3, and that's going to put 1 down here. And what you'll notice is that each of these roots is equidistant, and they are separated by the same amount all the way around. In this case, 120 degrees, or in radians, we're talking about 2 pi divided by 3. Now, DeMoivre's theorem for finding our imaginary roots works in a similar fashion, but instead of having to factor and use the quadratic formula, what we do is we start by saying if I have x cubed minus 8 equal to 0, then I have x cubed is equal to 8, and I can immediately change that into a complex number as 8 plus 0i. That means that I'm now looking at x equaling the cubed root of 8 plus 0i to the 1/3 power. And according to our rules, we just change this into our cis form. And so we're looking at 8 cis. And on the x-axis, we would have 0 pi, or 0 degrees, depending upon whether you're in radians or degrees. We would then take the 1/3 power. Now this is DeMoivre's theorem. So we have the cubed root of 8 cis. And we're now looking at 1/3 times 0 pi. Now what's different between the DeMoivre's theorem that we worked on before and this one is we're now going to add plus 2 pi k. This is then going to give us 2 cis, and we now have 0 pi plus 2 pi over 3 times k. And the k value that we're going to use is 0, 1, and 2. And you'll notice it's always less than the power that we're working with, which would be 3. And that makes sense because we're going to have 3 roots, just as we saw from this one over here. So we're going to find our first one by taking 2 cis, and then we have 0 pi. Notice that's the same one that's right here. That is just plain 2. Our second one is 2 cis, and now we add 2 pi over 3 to the 0, and we get 2 pi over 3. And our third one is 2 cis 4 pi over 3. Now you'll notice each of these correlates or corresponds to one of the 3 that we have here. And the only way that we can actively check to see if we got them right is to plug in and work backward. So we would have 2 cosine theta 0 pi plus I sine 0 pi. And our job would be to simply simplify, and we would do the same thing for this one and this one, and check to see if we got the same thing. In this case, we have 2 times 1 plus 0i. And you notice that just gives us 2. If we're working on this one here, we're looking at 2. Then we have the cosine of 2 pi over 3, which we know is a negative 1/2. And then we have plus root 3 over 2i. Notice that when we distribute, we get negative 1 plus root 3i. And that's our first root that we found in this group. Doing this one, we're then looking at 4 pi over 3, which gives us 2 times negative 1/2 for the cosine of 4 pi over 3. And then we have minus root 3 over 2i. When we distribute, we get negative 1 minus root 3i, and that was our third root that we found right here. So it isn't a difficult thing for us to find our imaginary roots as long as we follow this basic pattern. So keep in mind, we want to first take an a plus bi. We want to convert it into cis form, so r cis theta. Once we have that, we're then going to take the nth root, and the root can be any value, and this would then be 1 over n. We end up getting r to the nth root cis of 1 over n times our theta, and then it depends upon whether we're using radians or degrees. If we have degrees, we're going to add 360 degrees times k. That's the easiest of the choices. And the other option is or r to the 1 over n cis 1 over n theta plus 2 pi k. And that was like the one we just finished. And we find out all of our roots. So this is once again generally fairly easy. Let's take a look at 1 plus root 3. Let's make it harder. Let's go negative 1 plus root 3. So our first thing is to find r, and you'll notice we get a 2. And then we're sitting in the second quadrant. We know we're going to have root 3, and our theta tends to come out as pi over 3 or 60 degrees. And that's giving us an answer that's down here. So we're going to have to add 180 degrees or pi. And that would then give us a theta that is 2 pi over 3 or 120 degrees. Now, depending upon the way you're doing it in degrees or radians, we would now have to decide, well, what do we want? Well, let's say that we want the fourth root. So we're going to find the fourth root of this value. That means I'm going to have the 2 cis, and I'm going to go ahead and I'm going to do it in degrees since I did the other one in radians, and it's to the 1/4 power. We're now looking at the fourth root of 2 cis 30 degrees plus 360 divided by 4 is 90 degrees times k. Notice how I did that. I took 120 degrees plus 360 degrees k, and I divided both sides by 4. That's multiplying by 1/4. I ended up getting the 30 and then 90 degrees. I now have the fourth root of 2 cis 30 degrees. There's my first answer. The fourth root of 2 cis 120 degrees. There's my second answer. The fourth root of 2, excuse me. I was going to put cis inside the radical, and that would not be correct. 2 cis. And now I'm adding another 90, so that gives me 210 degrees. And the final one would be the fourth root of 2 cis, and adding 90 gives me 300 degrees. Now, in order to find what these are in rectangular form, we simply use our 30-degree angle and our knowledge of the reference angles and our unit circle in order to simplify these just like we did before. Now, this is finding roots. You'll notice it is not difficult. You just have to make sure you follow the appropriate formula and the appropriate pattern, and then, depending upon what is asked of you, you then go forth and answer whatever is asked. If they want you to put them in rectangular and then graph them, change them into rectangular form by doing the fourth root of 2 times the cosine of 30 degrees plus the fourth root of 2 times the sine of 30 degrees, I think I said 40 degrees, 30 degrees times I. So try not to stress. Just remember, you can go back and forth between polar form and rectangular form, all you need to. But this makes it a streamlined process for finding all of our roots for any polynomial that we might have. Alrighty, that's my video for today. I hope this was useful. I hope it helped. If you liked it, please remember to click like. And if you have suggestions for me on how I can improve, please leave me a comment and I will do my best to improve the video. Thank you very much. Have a wonderful and fantastic evening. Take care, Hornets. Cheers. Bye-bye.